Okay, we're going to make a start on projectile motion. We'll start with the simplest case with our ball on flat ground. Starting from the origin, it's projected at some initial speed, say u, and at some kind of angle, say theta. Really keep in mind that u and theta for us right now are constant numbers, okay? Like a deep awareness of what is constant will be really helpful when we dive into the calculus. So we launch it and off it goes. It's worth noting here that in this simplest case, we'll ignore any air resistance as well. So that gives an easy starting point for our equations. Since the only force acting on the ball is gravity, the acceleration is purely downwards, and we would write this in vector notation as a equals 0, negative g. So nothing in the horizontal direction, and just gravitational acceleration pulling down, hence the negative. Note again here that g is also a constant number, okay? For us on the surface of the Earth, it's around 9.8 or something like that. Okay, so that's the acceleration vector, so that even though the ball is given some sort of initial boost of speed when it's thrown, it gets dragged back down and follows this parabolic arc, okay? Now, we haven't proven that it's a parabola yet, so that's a spoiler. But as usual, to proceed, we will integrate with respect to time to gather information about things like velocity and position. Okay, so let's integrate once to get the velocity here. In the horizontal direction, the integral of 0 is just a constant number, which we'll call c1, because we'll be dealing with a lot of constants. In the vertical direction, negative g is itself a constant, so when you integrate, he grows a t, and there's another constant at the end, say c2, to not get them mixed up. So how do we go about working out these constants? Well, something we've done heaps is to use the initial conditions, or any other given information like that, to sort them out. So it's worth having a closer look at the yellow vector, the one describing the initial speed the ball was launched at. We seem to be caring about its horizontal and vertical components separately, so we'll split him up into the horizontal and vertical components, okay? The horizontal one then must be u cos theta, and the vertical one must be u sin theta. Okay, hold on to this setup in the back of your mind, but before we use these things directly, I want you to see what exactly these green vectors are physically doing. So let's just focus only on the horizontal velocity. We said that he had to be a constant, meaning if we leave a sort of shadow of the ball here, this light blue one, I want you to notice that when we throw the ball this time, its shadow along the ground is moving at a completely steady speed throughout the flight. That's why the horizontal component of v is just a constant, okay? And what is that constant? Well, remember, this green vector down the bottom had an initial value of u cos theta, and we know it's constant, it doesn't change, so that means that c1 over here must be this exact value, u cos theta. Okay, looking back at the picture, let's track the vertical velocity this time. Since gravity is pulling down at a constant acceleration, a constant rate there, our equation tells us that the vertical velocity will decrease at a constant rate. So we can see as the ball flies, the vertical velocity vector is doing exactly that. Okay, it goes from pointing up to 0 to down. Okay, watch that again if you need to see that. Now, his initial value was u sin theta, and this should actually be the constant c2 as well. Why is that? Because c2 is what survives when t equals 0. That is, c2 must be the initial vertical velocity of the ball. So we get negative gt plus u sin theta for the vertical velocity. Alright, now for the position of the ball, which we sometimes use vector r for, we would integrate again. So for the horizontal component, u cos theta is just a constant, so when we integrate him, he just grows a t with a new constant at the end, say c3. Vertically, the same thing happens with u sin theta, but for the negative gt, we would have to go t square and divide by 2, so we get that. Notice there's yet another constant at the end. So this is what the position vector is tracking, and that's why the arc is indeed parabolic, because while the x value varies linearly with time, the y value varies quadratically, and there's your parabola. Okay, great. So what are these C3 and C4 constants? Well, again, they are the only survivors when t equals 0. But in this case, the ball begins at 0, 0, at the origin. So that means they both must be 0. And of course, if the ball began elsewhere, say you were chucking it off a cliff or something, they might not be 0, but in our case, they are. Okay? So what we've come up with are these three vectors telling you the position, the velocity, and the acceleration of the ball at any point during its flight. Now, the only variable controlling all three of these things, and in both horizontal and vertical directions, is t. That's the only variable in that whole setup there, the time of flight. Okay, so we now have the power to track where the ball is, how fast it's going, in what direction it's going, at any point in time during its flight. Okay, so say 1 second after launch, or 2 seconds after launch, and so on. Okay, so let's see what sorts of questions we can ask about this. One could perhaps be the maximum height of the ball. Okay, how tall does it go? So this length h here. The approach would be to think about what the physical situation tells you about that point in the ball's flight. Okay, we have no idea about how far away that point is in either direction, but if we track the velocity vectors, separated again by horizontal and vertical components again, then you'll notice that at the very top of the flight here, the vertical arrow has vanished because it has 0 vertical velocity at that point in its flight. So if we look across to the right at all those guys, we know that this negative gt plus u sine theta guy must be equal to 0. Remember here g is constant, it's gravity. U is constant, it's the initial speed the ball was thrown at, and theta is constant, it's the angle it was thrown at. So really, the time t is the only unknown here, and solving for it again will give us all the other information at this particular point in time, which we know is at the very top of the arc because that's the only place where the vertical velocity is 0. So let's do that. Okay, if the negative and positive add to 0, then gt must equal u sine theta. Then to get the time t, we divide by g. So this value of t can now be substituted wherever we like to find out all the other information about the ball when it is at the top of its flight. And what are we interested in? Well, we're interested in h, which is the vertical component of its position. So the ut sine theta minus gt square over 2. So we'll grab that guy, okay? And there's our t. We're going to sub the whole u sine theta over g into t. So there's one of them. And there's the other one. But he's being squared, so all the green guys coming from t here need to be squared as well. So we have two fractions here. Let's simplify them both separately first. So upstairs on the left, we have 2 copies of u giving u square. 2 copies of sine theta giving sine square theta, and the single g downstairs. On the right, just notice how the g upstairs will kill 1 copy of g downstairs, and everything else can just be brought across like that. Now, if you look at this carefully, we have a full copy of u square sine square theta over g, minus half a copy of the same u square sine square theta over g. So when you get 1 copy of something and you remove half of it, you're left with the other half. Okay, so u square sine square theta over 2g would be our result. And that is a final answer, okay? That's why I've been stressing an awareness of what is constant. If anything, even just to know when you're done, because everyone here is a constant, part of the initial conditions of the question. Okay, so that is the maximum height done. We could maybe ask for the horizontal range as well. Now, I won't work this one to completion. I might leave it for you to sort out. Look, for this simple setup, maybe the most efficient way would just be to use symmetry, because we know all about the top of the flight already, but sometimes a situation won't be totally symmetric, so we can't count on that. What information we know for sure at the end of the ball's flight, though, is that it ends on the ground. And that very often gives you something about its position. In our case, it would simply be that the vertical height, which is that ut sine theta minus gt square over 2 guy again, must be equal to 0. And when you solve this quadratic for the time t, you'll naturally get 2 answers because there are these 2 points at which the ball is on the ground. t equals 0 is surely a solution because it starts on the ground. So the other solution must be the point we're interested in. So that time t would correspond to the total time of flight of the ball, and you'd then feed that value of t into the horizontal component of the position, which would give you the range. So have a go at that. If you have a moment, see how you go. That's all for now. See you around.